about what would happen in an equation that would make the equation not be a polynomial. And the reason we need to discuss this is because the graphs that we're going to be graphing are going to be called polynomial graphs. So that means they cannot have exponents that are fractions. So my first little example under the knots is showing you that a polynomial can't have an exponent that is a fraction. So none of the graphs that we're going to do in this section will have exponents that are fractions. The next little term shows you that we can't have any variables inside absolute value. That would not be in a polynomial function or equation. We can't have any variables underneath a square root. We can't have exponents that are negative, and we can't have any variables that are in the denominators. That's kind of a good thing, right? Those kind of make our lives not so good. So anything that we've talked about in that not a polynomial, you will not see those at all in this section. And all of the rules that say these are rules for polynomials, they would only be rules for things that don't have fractional exponents, x's in the absolute value, and so forth. So now let's look over here at things that we can have in polynomials. This will make a little bit more sense now. So some people might think that the square root of 3 times x is not okay. But why is that okay? The x is not under the square root there. So those are just some little tricks. Sometimes they'll try to throw in a problem to try to get you to think it's not a polynomial. And why is the 1/5 x to the 4th okay? X is not in the denominator, the 5 is. Okay? And the negative pi x squared, some people think that's really weird, but pi is a number. Okay? It's just irrational. It never ends and it never repeats. So when we start talking about degrees, like the very next thing is the degree of a polynomial. That does not have anything to do with those things that we've circled in red. Okay? So when we're talking about a degree of polynomial, we're talking about things that have to be polynomials. So in my very first example, the degree of a polynomial is always the exponent that is the highest. So y'all see that in example 1, even though 7x to the 6 is not written first, which would be in standard form, the highest exponent in that polynomial would be 6. So we're going to be using that degree of the polynomial to tell us about the end behavior of our graphs. Alright, so the next thing that I've done is I've graphed some equations, and in your homework they'll graph some equations and they'll ask you whether they're polynomials or not. So don't get caught up in the word function here. They're not asking you whether these are functions, they're asking you whether these are polynomials. So let's look at the no's. Let's look at the 3 no's. Can anybody tell me in example 5? We'll go with example 5. What would be in the equation for the graph of example 5? Okay, are you looking at 4? Oh, a variable underneath the square root? You're right. So on example 5, y'all know that's a shooting star. So that would not be a polynomial because we can't have a variable underneath the square root. How about example 6? That would be the absolute value graph, and that would not be a polynomial. So everything we talk about polynomials wouldn't apply to that graph. And then lastly, number 4, you haven't graphed a lot of these yet, but this would be where we have a variable in the denominator. Okay, this would be where the graph can't touch the x-axis or the y-axis, as they're called asymptotes. That's because there's going to be some undefined value. And we'll study those graphs later on. So example 2 would be a polynomial graph. It would be a polynomial. And example 3 would be a polynomial, but the other ones would not. So when you're looking at the graphs, you're having to think about things that you have a little bit of knowledge on. So you're thinking about those things. X is in the denominator, x is under square root, x is in absolute value. Alright? So now we're going to talk about something that's really, really important. This is something that you're going to hear later on in your other math classes. It's called the leading coefficient test. the leading coefficient test. So before I go through the leading coefficient test, let me just page over to example 7, 8, 9, and 10, just so you can have some examples of some polynomials. So in example 7, the leading coefficient is 2 because it's the coefficient of the variable that has the highest exponent. We'll need to write these in order, highest to lowest. In example 8, the leading coefficient is negative 2. In example 9, what's the leading coefficient? 5. In example 10, the leading coefficient is negative 5. So the leading coefficient is always the coefficient of the variable that has the highest exponent. And if you write your polynomial in standard form, you'll always write your highest exponent term first. And you need to get in the habit of doing that. So we're going to talk about the leading coefficient test. It says the leading coefficient is the coefficient of the variable with the highest degree. And then I've broken this down into two areas. If the degree, that means the highest exponent, if it is even, and this is what we saw from our T-chart graphs, if the degree is even, and I abbreviated leading coefficient LC, and LC is positive. If the degree of your polynomial, which is the highest exponent, is even, and your leading coefficient is a positive number, then both ends of your graph are going to go up. And this book likes to use rise and fall. So it likes to use rise for going up, fall for going down. It means the same thing. I don't care what you put. As long as you tell me both ends go up, you can say both ends go up. You can say both ends rise. If the degree is even and the leading coefficient is negative, then the ends are still going to go in the same direction, but they're both going to go down. Again, we're not sure what's going to go on in the middle of that graph. We'll have to find some x-intercepts, some y-intercepts. Talk about the number of turning points to figure that out. If the degree of the polynomial is odd, okay, that means the ends are going to go in opposite directions. If the degree of the polynomial is odd, if the highest exponent is an odd number, the ends are going to go in different directions. If the leading coefficient is positive, then the right-hand side goes up and the left-hand side goes down. If the leading coefficient is negative, then the right-hand side goes down, so the left-hand side must go up. It's a little bit harder to memorize the ends of the odd graph. So always go with the right side. If the leading coefficient is positive, the right side goes up, so the left-hand side must go down, and then vice versa. Okay? You're going to want to be able to look at your equation and decide whether the ends both go up, both go down. If they go in opposite directions, you're going to want to know which ends go up and down. Okay? You don't want to rely solely on making a T-chart. You want to be able to determine a little bit about what the ends of the graph are going to do by looking at the equation. Any questions about those? All right, and so then the next part of your homework is going to give you examples. It's going to say use the leading coefficient test to determine the end behavior. So in example 7, to yourself you would say the degree is odd. The degree is 3 and it's odd. The leading coefficient is positive, so that means the right-hand side goes up and the left-hand side goes down, and sometimes I draw that and then I write my answer, and this book writes it as the graph falls to the left and it rises to the right. So in example 8, you would look for the highest exponent. The highest exponent is 3. That is odd. That's called your degree. Your leading coefficient is negative, so that means the right-hand side is going to go down and the left-hand side is going to go up, and you'll write rises to the left and falls to the right. You can even just draw the arrows if you want to. Okay, I'll just take the arrows. Example 9, the degree is even because the highest exponent is 4. That means the ends are going to go in the same direction. The leading coefficient is positive, so that tells us that both ends go up. And you can write the ends going up, or you can write left rises and right rises. And then the last one, the degree is even, but the leading coefficient is negative, so that means both ends go down, okay, or both ends fall. Any questions about how you look at a polynomial and use the leading coefficient test? All right. The last part of your homework will be the most complicated. It's going to ask you to find the zeros. Okay? Underline the word zeros. All right, zeros are x-intercepts. You may also know these as solutions. So when they're asking you to find zeros, they're asking you to find where the graph crosses the x-intercept, which is also considered solutions to the equation. It's asking you to find the multiplicity, which you've never seen before. And it's asking you to state whether the graph crosses the x-axis at each intercept or whether it touches the x-axis and turns around. Whether it touches and turns around. So that's a whole lot of stuff. So let's kind of break it down. So they're going to start by giving you equations that are already factored. They're going to start by giving you equations that are already factored. So in example 1, your factors are 3, x minus 2, and x plus 5 squared. You need to know if the factor doesn't have an x in it, it has nothing to do with these directions. If the factor doesn't have an x in it, it doesn't have anything to do with the directions. Your factor has to have an x in order to be an x-intercept. So you won't look at the 3 at all. Okay? So the first factor you really see is x minus 2. So either in your head or over to the side, you're going to set x minus 2 equal to 0, and you're going to solve. A lot of you will be able to just do this step in your head. Okay, so it's already factored there. You'll just set it equal to 0 and you'll solve. It's like getting a solution. It's the same thing as getting an x-intercept. So that's where I'm getting x is equal to 2. Then it wants the multiplicity. The multiplicity comes from how many times the factor x minus 2 occurs. Okay, so you just look back at the problem. That x minus 2 only occurs once, so we say the multiplicity is 1. The multiplicity has to do with the factors. If the multiplicity is odd, then that is an x-intercept where the graph will just cross the x-axis. It'll just cross the x-axis. Go to the next factor. The next factor is x plus 5. Set that equal to 0 in your head and solve, and that gives you x is equal to -5. Look back at your exponent on your factor x plus 5. Is it even or odd? Or what is it? What is it to begin with? 2. So your multiplicity of that factor is 2. That's the exponent. If your multiplicity is even, then that's an x-intercept where your graph touches and turns around. So maybe we want to add this to our notes. If multiplicity is odd, then that's an x-intercept where your graph is just going to cross the x-axis. If your multiplicity is odd, then that's going to be an x-intercept where your graph just crosses the x-axis. If your multiplicity is even, that's going to be an x-intercept where your graph touches and turns around. And I like to abbreviate that T and T. To give you a visual, I'm going to show you what it looks like when the graph just crosses. So if the graph just crosses here, then at this green point, that's just where it crosses. If the graph touches and turns, it'll come up, it'll hit the x-axis at one point, and then it will just turn back around. It'll touch the x-axis and turn back around. So here is an example of touches and turns. Here's an example of where the graph touches and turns on the x-axis. And then here's an example of where the graph just crosses the x-axis. That's going to be important because we're going to have to be sketching in the middle of our graphs. We're going to know what the ends are going to do, but we're not sure what the middle of the graph is going to do. We'll be able to find the x-intercepts, and we'll need to know when the x-intercept just crosses or if it's an x-intercept where the graph touches and turns. So glance down at example 12. It's already factored for you. You don't look at any factor that doesn't have an x, so you won't look at that 3. X plus 3, x minus 5, and x plus 1 all occur one time. So y'all see all the multiplicities are 1. And that means they all cross the x-axis. They don't touch and turn. You'll just set each one of those equal to 0 to find your x-intercepts. All right, let's page over to the very last one because it's not factored. So in example 15, you'll have a few homework problems where your polynomial is not factored, and you'll have to go back and remember how to factor. So what's the clue that we're grouping here in example 15? There's 4 terms, and when we have 4 terms, we usually group the first 2 terms and the last 2 terms. You factor out the GCF of the first 2 terms, which is x squared. You factor out the GCF of the last 2 terms, which is -9. Then you get that little common group of x plus 5. You factor out the x plus 5, then the x squared minus 9 factors again. And finally, you get your 3 factors, x plus 3, x minus 3, and x minus 5. It won't matter what order your factors are because you're multiplying. And then you set each one of those factors equal to 0 to get your intercepts. All the factors occur once, so the multiplicity is all 1. If the multiplicity is odd, then that's just a place where the graph crosses the x-axis. If the multiplicity would have been even, then that would have been a place where the graph touched and turned.